College Algebra, Chapter 3, Section 6, Topics in the Theory of Polynomial Functions, Part 1. First, we're going to talk about the intermediate value theorem. This is a very useful theorem. It says that if p of x defines a polynomial function with only real coefficients, and if, for real numbers a and b, the values of p of a and p of b are opposite in sign, then there exists at least one real zero between a and b. In other words, if you look at this graph, we have two x values, a and b. So you find the y value that matches with a and you get a positive number. Then you find the y value that matches with b and you get a negative number. What the intermediate value theorem says is that this means that somewhere between a and b, the graph had to have crossed the x-axis. Because it went from a positive y value to a negative, it must have crossed 0 at some point. And here's an application of that. We're going to show that the polynomial function defined by x cubed minus 2x squared minus x plus 1 has a real zero between 2 and 3. All you're going to do is you're going to put 2 into this function and then 3 and get an answer for each. Why don't you pause the recording and try that and then resume the recording and I'll show you what we do with these numbers. Okay, when you put in 2, you get -1 for your y value. And when you put 3 into the expression, you get 7 for a y value. Since the sign changed from negative to positive, somewhere between 2 and 3, the graph must have crossed the x-axis. And so there is a zero, a real zero, somewhere between 2 and 3. Looking at it on a calculator, we can see that indeed the graph does cross the x-axis somewhere between 2 and 3. And we can verify that by the table. You see a sign change, and actually they've got the table set where it goes in very small increments of 1/1000th here. And you can see that that sign change takes place somewhere between 2.246 and 2.247. If p of a and p of b do not differ in sign, it doesn't necessarily mean that there is no zero between them. So it doesn't really tell you that there's not a zero, it just tells you if you know for sure there is. It could be that the sign doesn't change because it dipped below the axis and then came back up in between the two numbers. So remember, it doesn't mean just because the sign doesn't change that there is no zero. What it does tell you is that there is definitely a zero if the signs do change. All right, now we're going to be doing a little polynomial division, which we have done in both Algebra 2 and Algebra 3. So, tell you what, I'll walk you through this one. If you really want to try it yourself and see if you remember, feel free to pause the recording. But otherwise, we'll just talk through it. So we set the problem up. We make it look like long division. We have x minus 3 into 3x cubed plus 0x squared. Remember, when you have a missing power of x, you must put in a 0 placeholder for it, and that is true whether we're doing polynomial long division, which is what we're doing now, or synthetic, which we're going to talk about in just a little bit. So we have the 0x squared minus 2x plus 5, and the first thing we ask ourselves is, what is 3x to the third divided by x? In other words, what do I need to multiply x by in order to get 3x to the third, because we want that part to go away? The answer is 3x squared. So in the second setup here, you see that we have 3x squared on the top. We multiply 3x squared by x and by -3, and that gives us 3x to the third minus 9x squared, and we subtract. Be very careful with your subtraction. When we do, the 3x to the thirds go away, and we're left with 9x squared. And now we do the same thing. We do it all over again. We bring down the -2x, and we're going to ask ourselves, what do we multiply x by to get 9x squared? I'm going to proceed to the next slide where the rest of more of the problem is worked out. So the next number we're going to use, the next term is 9x. We multiply 9x times x minus 3, and we get 9x squared minus 27x. Again, we subtract. -2x minus 27x gives us 25x, and we bring down the 5. And finally, we ask ourselves, what do we multiply what do we multiply x by to get 25x? And that's going to be 25. So we have 25x minus 75, subtract, and we have 80. And that 80 is our remainder. So the answer to the division problem is 3x squared plus 9x plus 25 with a remainder of 80. We can also write the solution this way. 3x to the third minus 2x plus 5 over x minus 3, because remember a fraction is a division problem, equals, here's our answer, 3x squared plus 9x plus 25 plus remainder 80 over divisor x minus 3. Okay, so here it's stated a little more formally, if the degree n polynomial p of x is divided by x minus k, then the quotient polynomial, and you could see them labeled up there in our example, q of x, has a degree of n minus 1. And the remainder r is a constant and may be 0. The complete quotient for p of x over x minus k may be written p of x over x minus k equals q of x plus r over x minus k. That's exactly what we have written there. The p of x over x minus k is the 3x to the third minus 2x plus 5 over x minus 3. The q of x is our polynomial part of our answer, 3x squared plus 9x plus 25. R stands for remainder, and x minus k is again that x minus 3. Now, we are going to start making this process a little shorter. And again, if you remember from last year, when we can do synthetic division, it is a shorter process, but you must be dividing by x minus k. It must be x minus a number or x plus a number. You can't have a power on x in what you're dividing here. Okay, this is kind of showing you where the synthetic division comes from. What we did is we pretty much put 1 in for all of our variables. And you could see in doing this how the diagonal there is just kind of all the numbers that we used with the 0, the -2, and the 5. We're really writing things multiple times. So in order to shorten things up a little bit and not have to write so much, we do what's called synthetic division. Example of synthetic division. Now what we did is we put the 3 on the outside, and it was x minus 3, so you always go with the opposite sign. We put the coefficients of the polynomial we're dividing into 3, 0. Remember we had that placeholder, -2 and 5. And then to remember the process, what you do is you bring the first number down, so the 3 comes straight down. You multiply it by the 3 on the outside, so 3 times 3 is 9. And then we add 0 plus 9 is 9, and then do it again. 9 times 3 is 27. -2 times 27 is 25. 25 times 3 is 75. 5 plus 75 is 80, and that gives us the answer that we got before. Again, this is called synthetic division. Okay, so we're going to try an example. Now, I'd like to encourage you, see if you remember this from last year. Pause the recording, give it a try, resume the recording to check your answer, and we'll go through it. All right, so what we're going to use is we're going to use -2. That's going to go on the outside, as you can see. And then we've got the -2, we've got the little bracket there, and then we have 5, -6, -28, and 8. The first thing we do is we bring the 5 straight down. Then we multiply the 5 times -2, we get -10, and that goes under the -6. And we add -6 plus -10 and get -16. Let's see if you remember what to do next. Okay, next we multiply the -16 times the -2, and that gives us 32. -28 plus 32 is 4. Now multiply the 4 times -2. 4 times -2 is -8, and we get 0. So 5x to the third minus 6x squared minus 28x plus 8 over x plus 2 equals 5x squared minus 16x plus 4. Notice that we've lowered our power by 1 because we divided x to the third by x, so we're going to have an x squared, and we have no remainder this time. When we have no remainder, it means that what we divided into the polynomial was a factor. A factor is a number or an algebraic expression that divides evenly into another number or algebraic expression. Which brings us to the remainder theorem. The remainder theorem says if polynomial p of x is divided by x minus k, the remainder is equal to p of k. In other words, we're going to use the remainder theorem in synthetic division to find p of negative 2 if p of k is negative x to the fourth plus 3x squared minus 4x minus 5. Now, one thing you can do is put the negative 2 in for x and solve, but we're going to use the remainder theorem. We're actually going to divide the polynomial by negative 2 using synthetic division, and the remainder is our answer. You can do it both ways and verify that it works. Pause the recording, give this a try, and resume the recording to check your answer. So here we have our synthetic division. Notice we bring the negative 1 down. We multiply it times negative 2, and we got 2. Don't forget to put that 0 placeholder in because we're missing an x to the third. We add 0 plus 2, which is 2. Multiply by negative 2, we get negative 4, and so forth. And then we find that we have a remainder of negative 1. Well, that means that if you were to take negative 2 and put it into the original expression, your answer would be negative 1. The remainder that you get by dividing the number into the polynomial through synthetic division is the same as what you get when you put the number into the equation for x and solve. Now, where this helps us is we can check and see if what we have is actually a factor. Okay, so it says decide whether the given number is a 0 of p. Pause the recording and give this a try and resume the recording to check your answer. Okay, so we're dividing, and for a, we get 0 for our remainder, and that means that 2 is indeed a 0 of the polynomial because we have no remainder. For b, we do negative 2, and we get a remainder of negative 19. That means that negative 2 is not a 0 of p because we did not get 0 for a remainder. Here's looking at it graphically. What they did was they put in for y1 the p of x in part A, and for y2 the p of x from part B. And then they told the calculator to put in 2 and negative 2 for each of those respectively. And you see we got the same answers as we did when we did the problem with synthetic division. Okay, now we have the factor theorem. It says from the previous example, we have that the polynomial divided by x minus 2 gave us x squared minus 2x plus 5, which means that the polynomial equals x minus 2 times x squared minus 2x plus 5, indicating that x minus 2 is a factor of p. This is kind of repeating what we said before. Anytime you divide one polynomial into another and you get a 0 remainder, then that polynomial you divided into it is a factor of the larger polynomial. So the factor theorem says the polynomial p of k has a factor of x minus k if and only if p of k equals 0. In other words, if you can substitute that number into the polynomial and you get 0 for your answer, then it is a factor. So we're going to determine whether the second polynomial is a factor of the first. Give this problem a try, pause the recording, and resume the recording to see how you did. So we're going to use synthetic division, and our k is going to be negative 2. Remember, when they give you the factor, the x plus 2, you go with the opposite sign. If they give you the number, as opposed to x plus or minus number, if they just give you the number, then you keep the sign. And here we're using synthetic division, and we get a remainder of 0. So we have that when you divide x plus 2 into 4x to the third plus 24x squared plus 48x plus 32, you get a result of 4x squared plus 16x plus 16, which means that x plus 2 times 4x squared plus 16x plus 16 equals 4x to the third plus 24x squared plus 48x plus 32. Now, consider the polynomial function, p of x. We're going to show by synthetic division that -2, -3/2, and 1 are zeros. Then we're going to write it in factored form. We're going to graph it in a suitable viewing window and locate the x-intercepts. And then we're going to solve the polynomial equation, 2x to the third plus 5x squared minus 6 equals 0. Give this a try. It may feel a little repetitive, but there is a point to it. Pause the recording, give it a try, and resume the recording to check your answer. Okay, so first of all, what we did was we verified by using synthetic division. Now, we divided the -2 into it at first, and we got 0 for a remainder. Notice what we did. Instead of dividing -3/2 into the original, we divided it into what we got after dividing into -2. And you can do that. If you divide one number in and you get 0 as a remainder, then when you go to check the next one, you can use the new form of the equation that you got. So we're going to be dividing -3/2 into 2x squared plus x minus 3. And we get a 0 remainder again. And then finally we check 1, and that works as well. So we know that all three of these are indeed factors. And notice something else by doing this. That last little number we got there, that 2, that's our constant factor. So that's going to go in front of the parentheses. So we're going to have 2 times x plus 2. Remember, it's x minus -2, so that's x plus 2, times x plus 3/2 times x minus 1. And that is the factored form of p of x. Graphing it on the calculator, we can verify that -2, -1.5, and 1 are all intercepts. That just happens to be the numbers that we used when we did the synthetic division. And the solution set, because the zeros of p are the solution set of p of x equals 0, the solution set is -2, -3/2, and 1. The point of this is to show you, or to reinforce, that x-intercept 0 solutions, these are all the same x values. They're all related. They all mean the same thing. Okay, division for any two polynomials. We have a division algorithm that says, let p of x and d of x be two polynomials with the degree of d of x greater than 0, but less than the degree of p of x. Then there exist unique polynomials q of x and r of x such that p of x divided by d of x equals q of x plus r of x over d of x. This may look familiar. It's actually the same thing we've been saying since really the beginning of this section. The polynomial divided by the divisor equals the quotient plus the remainder over the divisor. It's exactly what we've said before. This is just putting it in formal math language. R of x can either be 0 or the degree of r of x will be less than the degree of d of x. So try dividing this. Pause the recording, give it a try, and resume the recording to check your answer. By the way, do not use synthetic division because you do not have this in the proper form. You must use long division on this problem. Okay, so we use our long division and we get 3x minus 2 with a remainder of 4. Using our division algorithm, we're going to write it as 3x minus 2 plus -4 over 2x plus 3. Now try this one, and again, you must use long division. Pause the recording, give it a try, resume the recording to check your answer. Okay, notice that our divisor is missing an x term, so we have to put a 0 in there. It's just a really good idea to do it. It can seriously mess you up, especially if you're not really solid with the division, so please make sure you do that. And we can see that using our long division, we got 5x minus 4 with a remainder of 2x plus 2. It's okay to have the x in the remainder as long as the power, the degree of the remainder, is less than the degree of the divisor, which is underneath it, and it is indeed less. So we have 5x minus 4 plus 2x plus 2 over x squared plus 1. So this is of the video are going to be some problems you can try on your own. Pause the recording to try each one and then resume the recording to check your answers. Do this for the remainder of the video.